Okay, thank you, and good afternoon, everyone. As I introduce myself again, my name is Jesus Ortiz from the University of Miami, and today I'm going to present you the first part of our ongoing project together between the University of Miami and the University of Sherbrooke in Canada, that aim of assessing the flexural bond stress of new generation of GFRP rebars. This is a research group, Professor Nani from the University of Miami and Professor Ben Mokrane from the University of Sherbrooke in Canada. Okay, so the main objective of this first phase of this project was to evaluate the bond strength and the development length and lap-spliced length of GFRP rebars. This is because the current equation based on literature review have apparently could be conservative, others say that it could be over-conservative, others even say that is reliable enough to keep working with it. So based on this discrepancy between different research and different literature review, we decided to, in this first stage, address the equation with the current parameters that include in that equation. So the current parameters in the ACI 440.11 equation incorporate the concrete compressive strength into the bond strength, the FRP rebar size, the diameter of the rebar, the clear cover, and the embedment length. But if we compare this equation with other expression as the steel equation, we know that confinement reinforcement could be a really affecting parameter to the equation. The surface treatment in this type of elements, in this type of rebars, we know that we could have different types of surface treatment. The rebar modulus of elasticity, some authors have stated that could really affect through the axial stiffness, and the type of reinforcement as this equation was based mainly for GFRP rebars. But I mean, not right now in the 440 code, but in the 441R that includes basalt or carbon, we could have that difference between different type of rebars. So here first a brief introduction about what we're talking about. Is the bond strength that can be the maximum bond force that may be sustained by a rebar, and typically is accounted as the average bond strength. We assume that that distribution of stresses is uniform, so we assume that it's an average bond strength, but in reality this could change and this could vary depending on the real condition and the real stresses on that element. Also, other two definitions, embedment length and lap-spliced length. Embedment length could be both lap-spliced length and development length. Embedment length is simply the length that you embedded into the concrete, but the difference between lap-spliced length and development length is that the development length is that length that you need to transfer the stresses back to the concrete. The lap-spliced length is the length that you need to transfer those stresses between those two rebars that you are lap splicing, and again between the concrete. So it could be here a small difference between that. I'm highlighting this because in the current expression you just multiply by 1.3 in the most of the applications to change from development length to lap spliced length. So this is the current, or the equation that was based the current expression in the ACI 440. That was a study made by Brad Wambeke and Dr. Schill in 2006. So it was a expression based on a statistically based expression. So it's a statistically equation. It doesn't have a strength background, but more a statistically background. So this is very important in order to compare the results, but because when we found that some authors say that it could be over-conservative or over-conservative. When you're working with a statistically based expression, of course, you're going to have variability, and the ideal is that R squared in that model will be 1, so you always are in that, you always are targeting that result, but being statistically based, you will have some discrepancy also in the results. So the current expression considers the cover, the bar size, the embedment length, and the concrete cover. I add this K factor because you change between system from international system units or pound inches system. There is a factor there. So when they found this expression for the average bond strength, they equated that expression to the average bond strength. That is, when a simple free body diagram, you have this average bond strength, and they equated those two expressions, the average bond strength and the one that they found based on a statistically point of view, and they solved for the embedment length and incorporating some safety factors. They obtain this expression that is the one that we can found in the current 440 expression. So this is the embedment length, that is the length of embedment required, of the embedded reinforcement required to develop the required bar stress. So based on design assumption, or if you are designing, you will have a design tensile strength, and you try to reach that design tensile strength that is different from steel when you typically reach the yielding strength of the steel reinforcement. So what happened with this expression is that existing development length equation may yield to large values of embedment length. This is based on this is based on literature review that some authors said that could yield to challenges in detailing, congestion of rebars, and material usage when you compare to conventional steel when you have 30 dB. In this case, I mean in Ortiz, if we design it with this rebar, we will need a lap-spliced length of 140 times dB. So this is so far, no unified model is available that can be applied to general bond behavior GFRP rebars. If you go to available literature, you will see several different models, even several different equations. When we talk about the Europeans, the Japanese, the Canadians, each of those codes and guidelines have their own specific equation for lap-spliced and development length. And as I mentioned before, findings from the available literature present conflicting perspective regarding the reliability of the current equation. Some have said that is good enough, others have said that is under conservative, and sometimes over conservative depending on the parameters that you are evaluating. So in this first stage, we decided to target two specific parameters, the concrete cover and the embedment length, just to assess the reliability of the current expression to see if it's over conservative or under conservative, and see what is the next approach and the next step that we had to take. So we decided to go with a 4-point bending test. Typically, there is another parameter here that is the test setup. You could have a hinge beam, inverted beam, pull-out test, but we know the pull-out tests don't really give us the real stress in a typical flexural environment. So for the concrete cover, we have two concrete covers, 1.5 and 3/4 inch. This is to the minimum for a beam and a slab in ACI 440. And for the lap-spliced length, we decided to go with 40, 60, and 80. And as I mentioned, if we design it with this expression, we obtain 140 dB. So we were trying to be very optimistic here, and we decided to decrease that lap-spliced half the required length, because also of the available literature that say that they could be over conservative, the equation. So also we decided to go with on the reinforced concrete beam in order to be able to break the bar. The next step of this project was with an over reinforced concrete beam. You know that with FRP you could design for over reinforced concrete beam. We went with number 5 GFRP sun-coated rebars. Only a single rebar was considered because of the under-reinforced concrete design. We decided to put 2 rebars. We are going to have an over-reinforced concrete beam. 16 concrete beams were tested with 2 repetitions of each combination in order to minimize the variability in test setups, maybe during construction, concrete changes. So we made 2 repetitions of each combination. These are the properties of the rebar. Almost 200 psi of tensile strength, concrete cover of 40 megapascals, 6,000 psi, glass vinyl-ester FRP rebar, and of course it fulfilled with all the requirements with the current D8505 ASTM because of the also modulus of elasticity, more than 60 gigapascals. For instrumentation, we decided to go, of course, with LVDTs for measuring the deflections, strain gauges in the rebar. I know that this could be a little bit conflicting perspective because we are measuring the bond, but we are breaking the bond of the rebar. But we decided only to go with 3 small GFRP strain gauges in the GFRP. We tried to be very careful on the length that we were removing the sun-coated because, I mean, we needed to remove it in order to install the strain gauges, but we tried to be very careful to not to break that bond. But of course, that still will give us conservative value because we are breaking the bond of that rebar a little bit. We also notched the rebar at the end of the lap-spliced that in order to force that crack at that point. We realized after that that wasn't really necessary. I mean, the first crack was around that point, but we just decided to do like I think it was 10 millimeters notch, just to force that first crack at that point. We also install a small potentiometer on the end of the rebar. This in order to measure the slippage of that rebar and be able to associate that slippage value with a bond failure. All the tests set up and all the test construction also was made at the University of Sherbrooke in Canada. This was all GFRP, even the syrup, so I mean, it was lightweight. I was able to carry out that all by myself. So compared with steel, you will need a same in that. So we did a 4-point bending test. This is the results of the 80 dB lap-spliced with 19 millimeter clear cover. We decided to unload it after the beam crack, just to know if after the beam crack or after we measure 0.5 millimeters of slip. Just know if after the rebar slip, they're going to continue to have that movement if we unload the beam. After that, of course, we try to keep on the flexural cracks to know and be able to, after that, do an analysis with the cracks formation. And also, we try to categorize this failure. You know that in bond failure you could have either a splitting failure mode or a slippage failure mode. The slippage failure is when the bar just moves without any splitting, with any cracking of the surrounding concrete cover. But here, even though we don't see an horizontal crack, we saw a clearly bottom crack that allow us to classify as a splitting failure mode. So these are the results. We had 16 beams. 4 of them were control beams, continuous rebars. So even though that we had a FRP rupture design, at the end the failure was concrete crushing because of crushing near the load, the application of the load. But after we reviewed the strain gauges, the strain gauge was around 90%, 95% of the ultimate tensile strength. So we were almost there to be able to break the rebars in the continuous specimens. Also, the design approach, the theoretically ultimate moment versus the test moment was almost one. So the design philosophy and design approach was good in these cases. And here also we compare with the design moment. Design moment, you know that when you design on the reinforced concrete beam, the phi factor is 0.55. So here we can see that even though those rebars, those specimens 40 dB were almost one in that ratio between the test moment and the design moment. So here also where we can see the over-conservativeness of the design approach because of some variability of the rebar. So in that graph, we can see that, of course, the longer the lap-spliced length, the higher the capacity, and also we see the difference between the 19 millimeters clear cover specimens against the 38 millimeters clear cover specimen. Here are all the failure modes. All of them were classified as splitting failure mode. I know that in some of them you can see that horizontal splitting, but again, because we only have one bar, so the main failure plane was a bottom crack. The two control was, of course, concrete crushing. So then we can see the moment versus deflection curves. Here's something that we saw that we tried to evaluate all the data again because that was strange, that we didn't see any loss of stiffness due to the movement of the rebar. All of the lap-spliced specimens fail by splitting failure, so a bond failure. But if you see the slope continues similar until a failure. So that was something that catch our attention, because here an excessive deflection can be related with a bond failure, because we don't see any loss of stiffness due to the bond failure. Also, when you are designing, of course, for the 19 millimeters clear cover, you have a higher and deeper effective depth. So theoretically, you have a higher design moment. But because of the failure mode and being a bond failure, the 38 millimeters clear cover specimen had a higher capacity than the 19 millimeter clear cover. So sometimes you think that you could have the less cover, you have a deeper and higher effective depth. That smaller concrete cover will lead you to a bond failure, so it will decrease your capacity. This is the influence of the parameters. So we plot both concrete cover and lap-spliced length here. So first, the impact of concrete cover was evident, but was not enough data to correlate the changes in capacity due to the clear cover. If we assume that the capacity will continue with this relationship of almost 0.4 kilonewtons meter per centimeter, we will reach the 100 capacity with a lap-spliced length of 153 and 127 dB for the 19 and 38 clear cover specimen. So first, the expression given by the expression that the current equation is based is not enough for achieving the full capacity. And also, these 153 and 127 dB represent changes of 10% and minus 2% based on the 440. But this is based to achieve the 100% capacity. But again, when you work with the 440.11 equation, you are using that expression for designing. So when you design, you are incorporating some safety factors. Here the equation have safety factors in the guaranteed tensile strength. So typically and of course if you incorporate the environmental reduction factor, you are only working with around the 80% capacity of that element. So that lap-spliced length could be reduced to 1.20 and 90 dB of those specimens. When we measured the slippage, we saw some slippage in all of the lap-spliced rebars on the lap-spliced specimens. The graph shows continuous movement of the rebar in the initial, of the rebar after the initial beam cracking. So after the beam crack, we start evidencing some movement of the rebar. But the rebar slippage did not significantly impact the bond strength capacity, as we saw in the previous graph, that we didn't see any drop in that slope. I mean, we were hoping that when the rebar moved, or slope, the stiffness will be decreased because of that movement. But after we analyzed the results, we really didn't see any impact of that movement. Of course, there is some movement. The maximum movement was 5 millimeters, in the 80 dB specimen. But we were able to correlate that slippage with a specific bond failure, because we saw some studies that say that the maximum slippage was around 1 millimeter. After 1 millimeter, you are classified as a bond failure. But in this case, we were able to go even to 5 millimeters and then have a failure mode. So we were trying to correlate, but there was not enough data, and we also lose some potentiometers, so we didn't have data for the full 12 specimens. So this is something that we really want to measure and test in the future stages. Then when we compare with the ACI 440 expression, this is the graph for the 19 millimeters and 38 millimeters clear cover. Typically in bond failure, you have 3 stages. The first one is the slippage zone. Typically is defined or is limited to 20 dB or 12 inches. I mean, theoretically, before that, you have a slippage failure, so the code limits your development length to at least 20 dB or 12 inches. And after that area after that region, you have a splitting failure. So this equation is not really to get the bond strength, but to avoid the splitting failure mode. So after that 20 dB, theoretically this expression, the 440 expression, is the one that governs that area. And after that, you have the rebar rupture that you went theoretically, you could have the average bond strength. So in this case, we were expecting a splitting failure. We got splitting failure, but our points on average bond strength were below that expression based on ACI. So that means that the ACI could be under conservative. The average bond strength that you predict is a little higher than the real one. In this case, 28% lower of value than the one that you predict with the ACI expression. And for the 38 millimeters clear cover is 10% lower. Also here, something that we saw is that theoretically, when you equate those two equations, so this intersection should be the development length expression. But in this case, we have a difference. That's because when they obtained this expression, the 440 Wambeke and Carl Shield, they did a small study when they found that the guaranteed tensile strength could be equal or approximately 85% of the ultimate tensile strength. And this difference is because in our test, the guaranteed tensile strength was around 93-94% of the ultimate strength. So we can see this as a safety factor that they decide to incorporate it in the current equation. We did the same with the Canadians. So the Canadians present higher or smaller reliability than the current expression. This first stage didn't have any confinement reinforcement. This is only to highlight that the Canadians did incorporate that factor in their equation, but also their equation were less reliable than the current ACI 440 expression. So finally, some conclusion. First, so the rebar slippage in lap-spliced specimen had a limited impact. We wanted to correlate that slippage value with a bond failure, but we were able, because based on the data, that wasn't a way to go, and also because we lost some of the potentiometers, so we lost measurements there. Lap-spliced and un-spliced beam exhibit similar deflection levels. So again, we were expecting that after the cracking, you dropped that slope, but we didn't see that, and we really reassessed all the data because maybe ours or some from the team was made a mistake, but we also compare with some available literature, and they present some similar behaviors. So concrete cover significantly influenced the behavior. Lap-spliced also, of course, impact the behavior. Reaching the 100% capacity will have required longer lap-spliced length. However, accounting for all the strength factors, as the environmental factors, and as we saw the guaranteed tensile strength, we calculate lap-spliced length of 120 dB and 95 dB for the 19 and 38 millimeters clear cover specimen. So this represents reduction of 50% and 27% from ACI provisions. So here we can see two different ways of also see the available literature review. Is that the bond strength equation could be under conservative, but when you change to the lap-spliced length and the development length equation after incorporating all those safety factors, you go to a conservative side. So this is two ways also when you are interpreting the results also from available literature. You really need to see what equation they are really targeting and really assessing, because one could be under conservative, but the other, after incorporating all the parameters, could be over conservative. To final conclusions. Yeah, okay. Now for future work, so we also need to do more with different tensile strength, tensile models of elasticity, also different type of concrete, lightweight concrete, ultra high performance concrete, because we really didn't assess. Of course, the GFRP stirrup, we know that the GFRP stirrups could really affect the bond strength, and here GFRP stirrup, because some of the available literature work with the steel stirrups, and we know that 440 doesn't allow that. And we need to revise the expression, the current expression, to incorporate all these different things.